Okay, so now that you saw a proof by construction, namely the construction of the finite automata M to recognize the union of two languages A sub 1 and A sub 2, for which we had two finite automata, M sub 1 and M sub 2, let's take a look at a couple of examples. And I'm going to basically make these examples easy, and so as we just go along, I'm going to create these examples. And please disregard the kinds of languages that these examples recognize, especially because they may be just nonsensical languages, like for example the language that only has 8 ones in it, or only 0 ones in it, and so on and so forth, because I want to keep these automatons simple, so that I could go over a few of them with you and show you how they are to be set up and created, um, and I don't want to get ourselves too much bogged down into the idea of what these languages will be, because for any reasonable language, the automaton might expand to probably a dozen or so states. That may make it a little bit too much out of um, the kinds of things that would be helpful in getting the points across. So let's suppose that we have the state diagram for an automata that looks something like this. So we start with a state. Actually, let's make this a two-state automata. I can only draw. Okay, so let's make this a two-state automaton that the second state is actually an accept state, and let's say that this machine is in state Q sub 0, and then Q sub 1, and then so we go something like this. On 0 we go like that, and then on 1 we go back, and in here we're just gonna accept on both. On 0 actually, and then let's say that this will stay in state Q sub 0 with 1. So that's one automaton there, and then let's have, so this is automaton M sub 1, and then let's make automaton M sub 2 to be also a two-state object. And for this, let's make the start state an accept state. So let's call these R sub 0 and R sub 1. And then let's have this machine to go over 0 and 1 to this state, stay in here over 1, and then go back to state R sub 0 when it sees a 0. Okay, so these are my two machines, M sub 1 and M sub 2. So I know that since this is a finite automaton, then there is a language A sub 1, which is a set of all strings that this machine M sub 1 accepts, and same thing with the M sub 2. So the language of M sub 1 is A sub 1, and the language of M sub 2 is A sub 2. Now I used 0 and 1 as my input states, as my symbols from the alphabet for both of these languages. So now I'm interested in constructing an automaton M such that M recognizes the union of the two languages. So I have language A sub 1, which is a regular language, and language A sub 2, which is a regular language. Why? Because there is an automaton that accepts it. As I said, don't worry about what that language is. Because there's an automaton, I know that by definition there is a language that my machine accepts for both M sub 1 and M sub 2. So what I'm interested is to build from these two, to build an automaton, to construct an automaton M such that the language of M is the union of A sub 1 and A sub 2. Now the good news is that from the theorem 125, I already know that, oh, I did the intersection symbol. So from the theorem 125, I already know that the set of regular languages is closed under the union operation, which means that not only is the union of the two languages a regular language, I can build an automaton that would recognize it. The way that I showed you and I proved the theorem was by constructing the automaton for the union language. And as a part of that, what I did is I created the automaton in such a way that it would simulate my two automaton here simultaneously on every input. To do so, my machine should be able to, should be capable of looking at and recognizing and working with both transition functions and both states of these machines. So both with the states of Q, M sub 1, and the states of R, M sub 2. Now for simplicity, in the proof, I used like Q11 or Q1I and Q2J for the automaton M sub 1 and then for automaton M sub 2. In this case, for simplicity, I'm calling all these R and I'm calling all these Qs so that we wouldn't have to put up with two indices. We just use one index to work. So that's for simplicity. But that's not necessarily needed. So the way that I said I will build this machine is that I would create the set of states to be ordered pairs. And since they are ordered pairs, each state would have two pictures. One picture from automaton 1, one picture from automaton 2's states side by side simultaneously. So I can work with both of these states. So the first thing I need to do here is to build my formal definition of the first automaton. If you remember from last unit, the formal definition of an automaton M is a 5-tuple. And I call this Q sub 1. Or actually, let's call this Q, because I called all of its states Q. And sigma, the set of its alphabet. Then delta sub Q, let's call this. And Q sub 0 to be the initial state. And F to be the set of its accept states. So as a result of that, my Q is a set of the states, which is Q sub 0 and Q sub 1. My sigma is the set of symbols 0 and 1 for my alphabet. The delta sub Q is actually as a function from Q over to actually cross product, Cartesian product of it with the sigma over to Q. And F is the set of my final my accept states, which is the set of Q sub 1. So that is my automaton M sub 1. Let's formally define automaton M sub 2. So M sub 2 is a set, here I call it R, is a 5-tuple from set R, set sigma, set delta sub R, set R sub state R sub 0, and set F sub R, and let's call this F sub Q. Let's call this F sub Q. To be precise, And then my sets will be R is going to be the set of R sub 0 and R sub 1. Sigma is the same, so it's going to be 0 and 1. Delta sub R is a function from R, cross product with sigma over to R. And finally, F sub R here for my second automaton is R sub 0. This is my second automaton formal definition. Now I need to do a little bit more to build the functions too. So I'm going to build the function delta sub q here in a table, in a tabular format, because in this case it's easy to do. I have only two states and I can represent them. So the automaton has two states, q sub 0 and q sub 1, and it accepts two symbols, 0 and 1. So basically, actually, let's do something like this. Let's you know what, I will just write these out because this is our first example. I just want to be quite thorough to show you exactly what is going on. So on q sub 0, the model of computation for this device is that delta sub q on some qi, comma, some element, it's going to be some qj, right? So that is how this computation works. If I'm in q sub I, for some I is 0 or 1, and I see an element a, 0 or 1, then I go to q sub j, from q sub 0 or q sub j, according to this machine diagram up here. So if I'm in q, so basically the way that this works is something like this. The way that it works is something like this. So delta of q sub 0 and 0. Let's see, what is it? So delta of q sub 0 and 0 is this. You're in q sub 0 and you see a 0. So you go to q sub 1. So this is going to be q sub 1. Then delta of q sub 0 and 1. What is that? So q sub 0 and you see a 1. It stays in q sub 0, so that's going to be q sub 0. Delta of, and all these things are delta sub q's, by the way. So delta sub q of q sub 1 comma 0. So if you're in q sub 1, you see a 0, you stay in q sub 1. So this is going to be a q sub 1. And delta sub q of q sub 1 and 1 is, you're in q sub 1, you see a 1, you go back to q sub 0. Okay, so then see, so delta q sub 0 and 0 is this element here. So this is going to be q sub 1. And delta q sub 0 and 1 is this element here. So this is going to be q sub 1. Or q sub 0, just that guy. Then delta of q sub 1 and 0 is q sub 1. So q sub 1 and 0 is q sub 1. And q sub 1 and 1 is q sub 1 and 1. The last delta down here, so it's going to be q sub 0. So this is what this delta sub q does. So your machine, your first machine, your m sub 1 computes according to this sets down here. So then for the m sub 2, I'll do basically the same thing. So the delta of r's, which is from q cross sigma, so 0 and 1, and this time I've got r sub 0 and r sub 1. So I've got delta of r sub 0 and 0, delta of r sub 1 and 1, delta of r sub 2 sub 0 and 1, sub 1 and 1 and 0, and delta of r sub 1 and 1. Now, another way to look at these in light of the cross product, remember I said when you have a set A and you cross product with B, you get a set of I and J, where I is from A and J is from B, right? So that these R sub 0, 0, R sub 0, 1, R sub 1, 0, and R sub 1, 1 come from cross product thing. And let me just clarify these also to be a little bit more tidy. So R sub 0 and then R sub 1 and 1. Okay, so so now what is delta of delta R basically? The for m sub 2. So delta of R sub 0 and 0, which means that if we're in states R sub 0 and we see 0, what happens? So if you're here, if we are in R sub 0 and we see 0, we go to R sub 1. So this is going to be R sub 1. So therefore, R sub 0 and 0, this guy is going to be R sub 1. Then delta of R sub 0 and 1. If we're on R sub 0 and we see a 1, we go to R sub 1. So this is going to be R sub 1. And that's what we're going to do here. We're going to go to R sub 1 here as well. Now if we're on R sub 0 and we see a 0, so R sub 1 and a 0 goes back to R sub 0. So this goes to R sub 0. So this is R sub 1 and 0. That goes to R sub 0 and R sub 1 and 1, which is if you're on R sub 1 and you see a 1, you stay in R sub 1. So this is going to be R sub 1. And here we're going to stay in R sub 1. That is my transition table. That transition table for M sub 1, transition table for M sub 2, transition functions for M sub 1, and transition functions for M sub 2. So that's basically what I did here. Okay, so now I have my two finite automaton created. Now to create the finite automaton M, okay, again, remember M is also a finite automaton, and therefore it is a 5 tuple. Now let's call its set of states to be let's call it P, and sigma is its alphabet, and delta is its transition function, and its let's call its start state P sub 0, and its final state or accept states P sub F. And let's see what these are for us for this state. Now according to the theorem that I just built, I said in order for me to be able to simultaneously simulate my two machines, I need to be able to, at each state, to be able to access one state from M sub 1 and simultaneously one state from M sub 2. This is the way that I simultaneously work with the states. Therefore, if I make the set of states P here to be the cross products of Q and R, then each of the members of this set is going to be two elements, Q sub I and R sub J, such that Q sub I belongs to Q and R sub J belongs to R. This is, by cross product or by Cartesian product, is my way of being able to access both of the states of my both machines at the same time. So I create a state that represents each pair of the states of my machine, so I would have access to all of the possibilities. Now if I do this, then my P, my elements, my set of states is going to be in the form of pairs, ordered pairs. And so for example, then the first element would be the first element from Q sub 0, the first element from Q sub 0, the first set from Q sub 0, and then the first set from Q sub from R. So it's going to be Q sub 0, comma R sub 0, comma. Then for I keep Q sub 0, and now I make it pair with R sub 1, so it's going to be Q sub 0 and R sub 1. And then now I do Q sub 1 and R sub 0, so I'm going to do Q sub 1 and R sub 0, and then I'm going to make Q sub 1 and R sub 1. So Q sub 1, comma, R sub 1. Now notice that now for my state here, these will be my states. So my states will be a pair of the states from the original machine. But these are basically merely just names for me at this point, right? So now how does my machine look like? If I were to draw this machine, actually I probably should have used a different color. So from this point on, we're going to use the color black for these machines basically. So if I were to draw these machines, then here's how my machine would look like. Okay, so then my states for my machine is going to be this. It's going to be Q sub 0, R sub 0, and then Q sub 0, R sub 1, and then this one, Q sub 1, R sub 0, and then finally the last element, Q sub 1 and R sub 1. Now you might say, well, why did you put them in this order? I had no idea. I just put them in this order because I wanted to, and you could put them in any order you want because I haven't created the transition function yet, so I don't know which state is transitioning to which state at this point. If you order them in a certain way, then you will have less lines crossing and less transition arrows crossing. So you might order first the states and then build a transition function, or you might first build the transition function like the table down here, which I'll show you next, and then from there draw your diagram. So it's totally up to you, and it really doesn't matter. So now this is my set of states. So my set of states for my final combined automaton that recognizes the union of these two languages is going to be a set whose elements are pairs of states from M sub 1 and M sub 2. One state from M sub 1, one state from M sub 2 paired together, and that would create a state for my constructed automaton. So that's perfect. So I already created the P, and this is done. Now the next is to create the sigma. And the sigma turns out to be, in this case, very easy because both machines have the same sigma, and therefore the machine that recognizes they're combined will have the same language symbols, so it's going to be the same sigma. So my sigma is 0 and 1. Now so that's done. Now before I do my my delta, let's do the P sub 0, the initial state for this new machine. Now remember, I said that I wanted to simulate the two machines side by side, which means that my machine should go through symbols one at a time and then see what each of the machine does. Each of these two machines do. So what that means is that when I start, both of my machines start in their start state. So since both of the machines start in their start state, this will be the element from P, these states, which contains both Q sub 0 and R sub 0, the start states of my original machine. So P sub 0 is going to be the element that has both start states, because when I want this big machine to start is to simulate the start of the two smaller little machines that is simulating side by side. And since the start state of this guy is Q sub 0 and the start state of this guy is R sub 0, then the start state of P is going to be the one of these elements that has both Q sub 0 and R sub 0s in it. And it's going to be only this one. So this one has Q sub 0 and R sub 0. This one wouldn't, because it only has Q sub 0. This one has only R sub 0. And this one doesn't either have Q sub 0 and R sub 0. So this is going to be my element. So P sub 0, then according to this definition, then my P sub 0, or my combined machine, will start in the state Q sub 0, comma R sub 0. So that would be the start state of this guy. Now, before I do my transition function also, again, let's do the final states, because this is also easy at this point. Now, with the final state, we're at the other end of the string. Now we're finished with our computation, and now this machine has completed its computation and simulation of the two other machines that it did. So it must accept the string that is the union of the original ones, which means that it must accept if either one of these two accepted, which means that it should be in such a state that either one of these two are accepting, are in the accept states. So it should have a state that's still a pair, and in this case I call it Q sub I and R sub j, such that Q sub I is from the F sub Q and R sub j is from the F sub R. So my accept states are effectively the accept states. Actually, this is an OR. Okay, so my accept states are the states that contain either one of the acceptances. So if there are, if my state is a pair in which either one or both of the elements belong to one or both of the accept states of my original machines, then I accept. So this OR is very, very important. Now, according to this definition, then, my accept state will be one that has either one of the accept states here. So Q sub 1 is an accept state, and R sub 0 is an accept state. So Q sub 1 is the accept state for the first machine, and R sub 1 is the accept state for the second automaton. Therefore, out of these, the accept states are the ones that contain either Q sub 1 or R sub 0, or both. So let's see which ones contain Q sub 1. This one contains Q sub 1. This one has Q sub 1. And this one has Q sub 1. Okay, so I accept these. And also the ones that have R sub 0. So these ones have R sub 0. This one has R sub 0, right? So this has R sub 0. And this one also has R sub 0. So these states will be in the final state because they either have Q sub 1, which is the accept state of this machine, or R sub 0, which is the accept state of this machine. So so the accept states are Q sub 0, R sub 0, because R sub 0 was an accept state, and Q sub 1 and R sub 0, because both R sub 0 and Q sub 1 are accept states, and Q sub 1 and R sub 1, because Q sub 1 is an accept state. So this will be the F sub P. Now, as a result of that, then therefore, this is going to be an accept state. So we're going to need to make this a double, a double circle. So this is an accept state, so it's going to be a double circle. Then Q sub 1, R sub 0 is an accept state, so this is going to be a double circle. And then Q sub 1 and R sub 1 is also an accept state, so this is going to be a double circle as well. Okay, and also while we're at it, let's also specify our initial state, which is this guy. So initial state is P sub 0, Q sub 0, R sub 0, Q sub 0, R sub 0. This is going to be the initial state, so I specify that. Like so. So now I created my machine with its states created, which is the pairs here, the language, which is the sigma here, the P sub 0, the start state, which is the state that has both start states in it, and the accept states, which are the states in which either one or two of the pair of elements are an original accept state from the original machines. Now finally, the computation. The computation is basically simulating both of the computations. So when I'm in Q sub I and R sub j in some state of my machine, and I see an element alpha, then I go into the state in which the first state is the computation of my first machine, which is the delta Q of Q sub I over A. And the second element is the delta R for the second machine of R sub J over symbol A. So see, Q sub I for the first part of the pairs, you use the Q transition function. For the second part of the pairs, you use the R transition functions to calculate. And this way, you get a pair of states. Okay, let's take a look at and enumerate these and see how they look like. So I start with the delta of Q sub 0, R sub 0 over symbol 0. Next is delta of Q sub 0 for the second element, comma, R sub 1 and 0. Actually, let's do the 0 and 1s. This way it's easier to see. So I do the delta Q sub 0 R sub 0 for 0, delta Q sub 0 R sub 0 for 1, then delta Q sub 0 R sub 1 for 0, then delta of Q sub 0 R sub 1 for 1, and I have 4 more to go. Delta of the third element is Q1 R0, so Q sub 1 R sub 0 over symbol 0, delta of Q1 R0 over symbol 1, and finally the delta of Q1 R1s, and this needs to go over symbol 0 and over symbol 1. Okay, so now let's see what happens. Now this is a pair of state then. So we're going to do the simulations simultaneously. So what this means is that, actually I'll do this for the first few and I write it out, and then for the rest of it we just fly through it. So this R sub j goes to the second element right here. So then according to this calculation, then it's a pair of states like this, in which the first one is the delta Q for Q sub 0 and 0, my symbol, and then the second pair is the delta of the second machine R for R sub 0 and 0. Okay, now this is nice to see. Now let's take a look at this. I'm going to just put a red star next to this guy. So let's take a look at this red star here. Let's see what this is. We know what this is from the first calculation. See, it is this guy. Delta sub Q of Q sub 0 and 0. What is it? It is Q sub 1. And then let's put another, let's put a, oh, I don't know, like a blue star, a green star for this guy. So what is this one then? Delta R sub 0, Q sub 0, R sub 0 and 0 is this, which is R sub 1. So this is going to be R sub 1. So now my pair that goes from Q sub 0 R sub 0 from this state over symbol 0 is actually Q sub 1 R sub 0, which is this element down here. So this is my transition. So my machine over symbol 0 goes and transitions from Q sub 0 R0 to Q sub 1 R0 according to this functionality here. Now let's do the second one for the transition over 1. So according to this function, I take the delta of q of the first state on the symbol, and that creates my first state. So it's going to be delta sub q of the first state, q sub 0, over the symbol 1, comma, delta sub r of the second state, r sub 0, and symbol 1. Let's see where they go. So my green star, delta sub q, q sub 0, 1, delta sub q, q sub 0, 1. Actually, this was red. This was actually a red element. So delta sub q, q sub 0, 1, which will be this element right here, which will be q sub 0, q sub 0 down here. So this is going to equal to q sub 0. So my first element is q sub 0. What's my second element? My second element is delta sub r of r sub 0, comma 1. Delta sub r of r sub 0, comma 1 is this guy. So it's going to be an r sub 1. Did I make a mistake? I think I did make a mistake. So this guy goes to r sub 1 too. You may start laughing at me now. It's been a long day. So this was r sub 1. This was r sub 1. So I need to justify this. There you go. So q sub 0, r sub 0 over 0 goes to q sub 1, r sub 1 for 0. And then for 1, q sub 0, r sub 0 over 1 goes to q sub 0, r sub 1. So that's going to be this. That's going to be this transition for symbol 1. Okay, so I knocked down this one. Now let's calculate the second symbol, and this time I'm going to use the red ink for the second calculations. So this is going to be delta sub q of q sub 0, comma 0, comma delta sub, actually, while we are here, so for the first element, which we are here, so we look at q sub 0 and 0, q sub 0 and 0 back up here, it was q sub 1. So the first element of the pair is going to be q sub 1. And then the second element of the pair is going to be delta sub r of r sub 1, comma 0. Delta sub r of r sub 1, comma 0, which is there. So delta of r sub 1 is that one, and it is r sub 0 there. So this is going to be comma r sub 0. So according to this transition then, let's make this blue. So I'm going to go from q sub 0, r sub 1, which is q sub 0, r sub 1, which is that guy, up here on the upper right corner. I'm going to go to q sub 1, r sub 0, which is right across the page. So it's going to go here, over 0. So see q sub 0, r sub 1. This upper right corner is going to transition to q sub 1, r sub 0 down the lower left corner over element sub 1, element 0. We'll have to do it for the element 1 as well. So I'm going to simulate the q with the red ink. So it's going to be delta sub q of q sub 0. It's going to be delta sub q of q sub 0 and 1. So what is it? Delta sub q of q sub 0 and 1 is the second element here. So that's delta sub q sub 0 and 1, which is q sub 0. So the first element of the pair is going to be q sub 0. So what's going to be the second element then? The second element is going to be delta r from the second machine of r sub 1 and 1. So r sub 1, comma 1. So let's see what that is. Delta of r sub 1 comma 1 is R sub 1. So this element is going to be R sub 1. So what we start from Q sub 0, R sub 1, which is the upper right corner down up here. So our start state is here, our current state is here, the next state is Q sub 0, R sub 1, Q sub 0, R sub 1, which is the same state. So over symbol 1, this state is going to transition back to itself. Because we go from Q sub 0, R sub 1 here to Q sub 0, R sub 1. So with C of 1, we stay in that state. Let's go, and I'm just going to fly through these rest of them. So I want to see Q sub 0, Q sub 1, R sub 0. Q sub 1 and 0, which is Q1 here. So this is going to be the delta sub Q of Q sub 0 and 1, which I already have it here. It's going to be a Q sub 0. And then the green element is going to be delta of R sub 0 and 0 R. So delta R of R sub 0 and R 0 is R sub 1. So this is going to be R sub 1, which means that from state Q sub 1 R sub 0, which is right up down here, R sub Q sub 1 R sub 0, I'm going to go back to Q sub 0 R sub 1, which was up here. So I'm going to transition back there over as 0. Okay, and then again the red state is going to be delta Q of Q1. Wait a minute. It should be Q sub 1 1. Q sub 1, Q sub 1 and 0. I'm confusing myself, aren't I? It has been a long day. So delta of Q sub 1 and 0. So Q sub 1 and 0 was Q sub 1. So this is going to have to be Q sub 1. And I have to just fix this. I thought there was something wrong with my calculation there. Okay, so again, I apologize. So Q sub 1 over element 0. So Q sub 1 over element 0 goes to Q sub 1. So go to Q sub 1 R sub 1. And therefore, this is my transition. There. Okay. Yes, definitely. You can laugh at me now. So then again, delta Q of Q sub 1 comma 1. So delta of Q sub 1 comma 1 is Q sub 0. That is it. So this is going to go to, I'm going to double check again. Q sub 1 1 goes to Q sub 0. There we go. And then for the green state, it would be delta R of R sub 0, its second element, and 1. So what is R sub 0 1? R sub 0 1 is R1. So I'm going to go to Q sub 0 R sub 1. So from Q sub 1 R sub 0, which is this state, I'm going to go to Q sub 0 R sub 1, which is this state, for symbol 1. Okay, so Q sub 0 R sub 0, symbol 1. So Q sub 0 R sub 0, Q sub 1 R sub 0 to Q0 R1. Q0 R1. Perfect. There's only 2 more left, so we are going to keep going. So we're going to get delta sub Q of Q. Wait a minute, what is this? Q sub 1. So Q1 and symbol 0. I need a bigger screen. So delta of Q1 and element 0. Delta of Q1 element 0 is Q1. And then the green state is gonna be the delta R of R1 and element 0. So delta of R1 element 0 is R0. Alright, so then therefore from Q1R1, which is this bottom right corner, we go to Q1R0, which is the bottom left corner for the 0 transitions. And finally, and I'll do this all in blue, so it's gonna be delta Q of Q1 1 and delta R of R1 1, which is gonna be Q11 Q0 and R11 R1. So it's gonna go there. So Q1 R1 goes to Q0 R1, which will be up here. So that's gonna go with element 1. So this is how your final, and here we are. We're done. So this is my final machine as described by the equations and as described by the um, the transition diagram. I start with Q sub 0 R sub 0. For 0, I go to Q sub 1 R1. For 1, I go to Q sub 0 R1. So that. And then Q sub 0 R1 over 0 goes to Q sub 1 R0. Over 1 goes to Q sub 0 R1. So it stays there. Then Q sub 1 R sub 0. Q sub 1 R sub 0, the bottom left corner. Over 0 goes to Q1 R1, which is the bottom right, and then over 1 goes to Q0 Q1 R1. So Q1 R0 over to 0 goes to Q1 R1, with 1 goes to Q0 R1, upper right corner, and so on and so forth. So you can read the rest of it. So that's how it is done, basically. And then let me just draw the diagrams also, or rather the table also, to show you exactly how the tables are drawn, which tables come from effectively my functions here. So my original states are the pair of states. So Q0 R0, Q0 R1, Q0 and Q1 R0 and Q1 R1. So these are my original states, and then my inputs are 0 and 1, and this is my delta P. So Q0 R0 with the 0, which is the first one up here, it goes to Q1 R1. So I'm going to draw this Q1 R1. Then Q0 R0 over 1, which is the second one, goes to Q0 R1. So it's going to go to Q0 and then R1. Then Q0 R1 over 0, which is the third one here, goes to Q1 R0. Goes to Q1, comma, R0. And then Q0 R1 over to 1, which is the fourth element down here, is going to go to Q0 R1. Then Q1 R0 with the 0, Q1 R0 with the 0, which is the fifth element here, goes to Q1 R1. Q1 R0 with 1, Q1 R0 with 1, the sixth element goes to Q0 R1. Then Q1 R1 over 0, it's the seventh element here, goes to Q1 R0. And then Q1 R1 over to 1 is the last element, and it goes to Q0, comma, R1. And this completes my construction of my finite automaton that accepted the union of both languages. Oh, and by the way, let's denote the final states with stars. So this is my original state, which I started with like a arrow pointing to it, and let's denote final state with stars. So Q0 R0, which is going to be Q0 R0. I'm not in it, so that's not going to be anywhere. Well, actually, it's right here, so that's one. And then the second final state is the Q1R0, which is that one, and then Q1R1, which is that one. And so these start elements are my final states. And of course, you can see that if had I put this Q sub 1 R sub 0 circle up here, I would have less arrows pointing to each other. So a simplified look of it, of this state diagram, may be something like this. That would be your first state. That would be your second state, and then you could put this third state and the fourth state kind of like that. So this state would represent your Q sub 0 R sub 0. This state would be your Q sub 0 R sub 1, and this state would be your Q sub 1 R sub 0, and this state would be your Q sub 1 R sub 1, and then therefore you'd see that you go with a 1 down here, and then you go with a 0 down here, and then from here with a 0 you go to it, with a 1 you get back from it, and then for this guy you go with a 1 to it, and then for these guys you go with a 0 and a 0 back and forth, and of course this stays in itself over a 1. And so you'd have a neater transition table in this case. But really, it really depends on how you would organize your transition tables and your states. But this is effectively one example of showing you the action, the results of the theorem 125 in action, and you see now how important it is. This is now a completely interesting, efficient, algorithmic way of building a finite automaton that accepts the union of the two languages. What you'll do is that you'll design the first language, define it completely formally, then you go and define the second language completely formally, and then you define and you take step by step of the proof by construction we did in the proof of theorem 125, the closure of your regular languages over the operation of union, and this algorithmically allows us to go ahead and build it. And of course, you see it's a tedious process, of course, because you have so many states and so many transitions and so many combinations that you have to take care of. You would have to be very, very careful about doing it right. I myself made at least half a dozen errors in building my model. So this really shows that and stands to show the fact that you'd have to double check and triple check and double check and triple check over and over to make sure that everything went right. And let me emphasize that this was a machine that was built with only 2 states. Each machine had 2 states, and we ended up with these many transitions that we needed to take care of. But then again, the flip side of it is that it was fairly straightforward and easy. There's nothing that you really need to do crazy stuff and juggle things. Although mathematically quite simple and easy, it will take time and practice to be able to build these machines. And practice you will get a lot of, let me tell you. But that would be for the homework assignment. So that's the example, and for the proof of the theorem that regular languages are closed under the union operation.